G'day, John here again. Welcome to another PyProx tutorial, helping you understand the impact of uncertainty in data and simulation. In the next few minutes, I'm going to teach you how to use Approximate Control-Variate Monte Carlo, ACV estimators for short, to compute the mean of a computationally expensive high-fidelity model prediction using an ensemble of unordered low-fidelity models with unknown means. I'll also teach you the general procedure that could be used to compute the variance of ACV estimators, and then I'll show you how to minimize the variance of any ACV estimator by optimizing the number of samples allocated to each model. Finally, I'll show you that multi-level Monte Carlo and multi-fidelity Monte Carlo are two types of approximate control-variate estimators, and that this knowledge can be used to better understand the properties of those estimators. ACV estimators take the form shown on this slide. Specifically, ACV estimators consist of a high-fidelity estimate Q0, computed using a set of samples Z0 plus a vector of weighted corrections delta. The entries of the vector eta are referred to as control-variate weights. Each correction is the difference between a low-fidelity estimator Qm, evaluated using evaluations of model M, at a set of samples Zm star, and another low-fidelity estimator using evaluations of the same model but on a larger set of samples Zm. The figure on this slide depicts the sample sets used by one type of ACV estimator, called ACVMF. Each set Z consists of a set of independent sample sets called partitions that are represented by different colors in the figure. The size of each set is denoted by capital P0 through capital PM, respectively. Viewers who watch my tutorial on multi-fidelity Monte Carlo estimators may recognize this form. In the theory section of this tutorial, I'll discuss the connections between multi-fidelity Monte Carlo and ACV estimators. ACV estimators can be constructed using 4 steps. Step 1 performs a pilot study to compute the quantities needed to determine the partition sizes P0 through Pm that are needed to minimize the estimated variance by optimizing the partition sizes in the vector P. First, a pilot study evaluates each model at the same set of samples P. Then these values are used to estimate the terms of the estimated variance shown in the equation. Specifically, we must estimate the variance of the high-fidelity estimator Q0, the covariance of this estimate of the differences delta, and the covariances between the deltas. The exact form of these covariances is dependent on a number of factors. I will show you how to compute each of these covariances in the theory section of this tutorial. But for now, it's sufficient to say that these terms can be computed for any vector or partition sizes without additional pilot evaluations. For example, when estimating the mean of a high-fidelity function, we only need to evaluate the covariance between models once. The formulas for approximating the model covariance is shown in green. Again, I want to emphasize that these covariances can be computed for a vector of partition sizes P without any additional model evaluations. But for curious viewers, look out for another tutorial giving more details on how to construct a pilot study, the effects of pilot quantity errors in the mean squared error of a multi-fidelity estimator, and the impact of the computational efficiency of multi-fidelity estimators in another tutorial. The second step needed to construct an ACV estimator minimizes the estimated variance subject to a computational cost constraint. Specifically, we enforce that the cost of constructing the estimator does not exceed a predefined budget Wmax. The cost of an estimator is a function of the number of times that each model is evaluated and the cost of evaluating each model once, which I denote W_M. For example, model 0 with cost W0 is only evaluated at P0 samples, so the cost of evaluating all samples allocated to model 0 is P0 times W0. Similarly, model 1 is evaluated on P0 plus P1 samples, and so it requires a computational cost of W1 multiplied by the sum of P0 and P1. The slide now shows the exact cost of the ACVM estimator with the sample set shown in the figure. Given a vector of optimal partition sizes P, step 3 randomly generates n+1 sets of independent samples calligraphic P0 through Pm from the joint density of the random variable Z. On this slide, I restate the definitions of the partitions that I introduced earlier for convenience. Step 4 evaluates all the models on the correct sets of samples. The independence of sets is depicted by the bottom left figure. Different rows and colors represent different independent sets. The sets used to evaluate each model are listed in each column. For example, the lowest fidelity model F2 is evaluated at the sets P0 through P2, highlighted by the black box. An example realization of such sets is shown in the middle figure. The model F2 is evaluated at all of the samples in these 3 sets, yielding the evaluations shown in black in the far right. Similarly, model 1 is evaluated on the partitions P0 and P1, yielding the evaluations shown in green in the far right figure. Finally, step 5 uses the model values we generated to estimate the mean of the high-fidelity model by constructing the estimator shown on this slide. First, the pilot study evaluations are used to compute the control-variate weights, the optimal partition sizes. Then we separate the evaluations of each model and use them to evaluate the 2 different estimators of each term in delta. For example, the light blue box surrounds the independent partition and associated model values used to evaluate Q1 Z1 star, and the green box surrounds independent partitions and associated values used to evaluate Q1Z1. In the first part of this tutorial, I enumerated the 5 steps needed to compute an ACV estimator. However, I skipped over many of the details, so in the remainder of this tutorial I'll try to fill in those missing details for you. Luckily, I've introduced many of the tools we need to compute properties of ACV estimators in my tutorials on control-variate estimators, so I really recommend you check those out. But for now, know that ACV and CV estimators are very similar. The main difference is that CV estimators assume that the statistic of each low-fidelity model is known, while ACV estimators use additional samples, that is relative to CV estimators, to estimate the low-fidelity statistics that are assumed known in CV models. At the highest level, the optimal control-variate weights and optimal estimated covariance of control-variates and approximate control-variate estimators are the same. The weights depend on the correlation of the high-fidelity estimator with each difference estimated delta and the covariance between the difference estimators. The optimal estimated variance depends on those same terms. However, once we plug in the form of the ACV deltas, the differences in the ACV and CV expressions begin to grow. For example, the covariance between the high-fidelity estimator and each ACV delta is shown on this slide. The second term in red is not present for CV estimators. The covariance between deltas for ACV estimators is given by the second expression. Only the green term is present in CV estimators. From this point, deriving expressions from each term depends on the type of statistic Q that is being computed. In the next few slides, I'll derive these two expressions when the statistic Q computes the mean of a function. First, we will compute the covariance between two mean estimators using two models M and N using different sample sets ZM and ZN. Using some tricks from the control-variate tutorials, we can write the covariance of the estimators as the sum of the covariances of each sample multiplied by the number of samples in each set Z. Then we split the sum into two parts, assuming that the size of ZM is smaller than the size of ZN. The first part contains the samples that exist in both sets Z. The second part contains the samples in ZN that are not in ZM. Next, we note that the covariance between the values of model M and N is only non-zero if those values are computed using the same samples. Finally, we simplify the sum, noting that the covariance between two of the values of models M and N computed at the same sample is just the covariance between the models. We can then substitute this final expression into the statistic agnostic expression for covariance between deltas on the previous slide to obtain the last formula on this slide. We're still not done though. The delta covariances depend on the number of samples in the sample set Z and Z star for each model. We can formulate different estimators by changing how these sets are constructed. First, let's consider the so-called ACVMF estimator. The sample set Z and the independent partitions they are made of are shown in the figure for 3 models. The general relationship between the set Z for any number of models is summarized by the conditions on the left. Plugging in these expressions to the formula we just derived gives the second equality. The slide uses color coding to show how each term in the general expression simplifies for the ACVMF estimator. For example, the intersection of the set ZM with ZN star is highlighted in green and is equal to N0. We just then collect terms and simplify. A useful exercise for the viewer is to make sure you can derive a similar expression for the covariance between Q0 and delta. Now let's compare the expression we just obtained for ACVMF mean estimators with MFMC mean estimators. The independent partitions making up the sample Z are shown in the new figure. The mathematical conditions used to make this figure are shown on the top left. Using these expressions, we see that unlike ACVMF estimators, the matrix representing the delta covariances for multi-fidelity Monte Carlo is a diagonal. This changes the relative performance of the estimators. I'll speak more to this soon. If you want to make sure you know how to derive estimated properties well, try to derive the expression on this slide and the similar one for the covariance between Q0 and delta. Now I want to show you how we can use the ACV framework to easily derive the optimal control-variate weights and variance of multi-fidelity Monte Carlo estimators shown in my tutorial on multi-fidelity Monte Carlo estimators. First, let's plug in the formula I gave on the last slide and the expression for the covariance between Q0 and delta. This yields the optimal multi-fidelity Monte Carlo weights that I gave in the MFMC tutorial. Now we can sub the same covariance expressions into the optimal variance. We then collect terms. Approximate Control-Variate Monte Carlo provides a framework to consistently analyze existing estimators and derive new estimators. In this tutorial, I introduced the ACVMF estimator. However, we can construct many other estimators by changing the sample partitioning used. For example, in this tutorial, I showed you how removing the crossed-out grey partition used by multi-fidelity Monte Carlo produces the ACVMF estimator and the different expressions from the optimal estimated variance that arise. The figure on the left highlights how the variance of ACVMF and MFMC estimators changes as we increase the number of low-fidelity samples while keeping the number of high-fidelity samples fixed. I presented a similar figure when comparing MFMC and MLMC in another video. The figure applies MLMC and MMFC to a model ensemble consisting of 5 polynomial models. The plot represents the decay in estimated variance as the number of samples used to evaluate each low fidelity model is increased. They're increased according to the vector-valued function g. As you can see, both MFMC and MLFC estimators converge asymptotically to the curve labeled CV1, which represents the estimated variance of a CVMC estimator that only uses the most correlated model. In contrast, the ACVMF estimator converges to the variance of the CV estimator that uses all low-fidelity models, which is represented by the line labeled CV4. The expression for the covariance between deltas can be used to understand this asymptotic suboptimality of multi-fidelity Monte Carlo. Specifically, as you saw earlier in the video, the delta covariance of an MFMC estimator is a diagonal matrix. This is because the partition was constructed so that each low-fidelity model is only used to improve the estimate of the low-fidelity statistic of the next highest fidelity model in the hierarchy. In contrast, the delta covariance of an ACVMF estimator is dense, so that each model informs all other models. In practice, we typically want to optimize the number of samples of an estimator to minimize its variance subject to a budget constraint. The general form of this optimization problem is shown on the slide. It is a non-convex problem that typically needs to be solved numerically. The most robust optimization strategy I've found is to use gradient-based optimization, for example a trust region method, using an initial guess obtained from the solution of an inaccurate global optimization algorithm. The use of the global optimization algorithm helps increase the chance of finding the global minima rather than getting stuck in a local minima. This procedure I described works for any ACV estimator used to estimate any statistic. However, in some cases the optimal sample allocation can be minimized analytically. For example, in previous tutorials, I introduced the analytical optimal solutions for MLMC and MFMC when estimating the mean of a high-fidelity model. However, note that if MLMC or MFMC are used to estimate statistics other than the mean, for example variance, then the optimal solution again must be obtained numerically. On the right, I compare the ratio of the estimated variance of MLMC, MFMC, and ACVMF estimators divided by the single fidelity Monte Carlo estimator of the equivalent cost. Values above 1 indicate that the estimator is more accurate than the single fidelity Monte Carlo. All methods are substantially more accurate than the single fidelity estimator. However, for this problem, the ACVMF estimator is most accurate. The relative performance of each estimator is problem dependent and will change if I use a different ensemble of models. So look out for a new tutorial that explains how to efficiently choose the best estimator for your problem using a pilot study. That brings me to the end of another PyProx video. Today I made 3 main points. 1. Approximate Control-Variate Monte Carlo provides a framework to analyze existing estimators and construct new ones. 2. In general, the optimal size of the sample additions that minimize the variance of an ACV estimator must be computed numerically, but there are some cases where analytical solutions can be derived. And 3. Finally, no one type of ACV estimator is best for all problems. See you next time.